Dear friends, Mass Aspirants is a community of mathematics students, research scholars, and teachers across India, initiated by myself in 2017. And we used to conduct online problem solving sessions and test series to help the students who are preparing for different national level competitive examinations like IIT JAM, CSIR NET, GATE, NBHM, etc. As a part of that series, today we have Miss Siddhi Balu with us to handle a session on selected problems from group theory. Miss Siddhi currently pursuing PhD at IIT Gandhinagar. She did her B.Sc from RJ College, Mumbai, and M.Sc from IIT Gandhinagar. She qualified CSIR NET during her MSc time itself and joined for PhD at IIT Gandhinagar. And her broad research area is commutative algebra. I would like to express my sincere gratitude to Ms. Siddhi for accepting our invitation and joining with us. I hope that today's session will be really helpful to everyone. Welcome everyone to this program. Welcome, Siddhi.
Thank you very much, sir, for nice introduction, and thank you very much for giving me this opportunity to conduct such a lecture here. As the title says, it is problem solving session in group theory. So I have kept this session a bit problem solving as well as a bit proof oriented session. So let's see how it goes. So let us start with what is a group. So we say a set G with binary operation dot, let's denote it by dot from G to G, is called group if satisfies certain properties. So such that if A, B, C in G, then A dot BC must be equal to A dot B dot C, and there exists some E in G such that A dot E is equal to E dot A is equal to A, and third property is that for all A in G, there exists B such that AB is equal to BA is equal to E. So this is the basic definition of group, and I did not mention, but I would like this session to be a bit interactive. So can somebody just give me one example of group of your choice?
Z plus.
Okay, Z plus. Z plus. So when we say Z plus, it is set of all integers with addition. And here we can see the associativity. So this is associativity. And here the identity E is 0 because we can see 0 plus any integer is again the integer itself. And for any given integer A, we can always find element B, namely minus of that integer, such that A plus B in our case is 0. So let us solve one problem in this direction. So let us say this is question 1. So if G be a non-empty set, and we satisfy this property that A, B, C is is equal to ABC for all A, B, C in G. And for any AB in G, the equations AX is equal to B and YA is equal to B have solutions in G. Then what can we say about this G? I mean, whether this G is a group or not. So
Group.
can hello?
It's a group.
Yeah, so can you just quickly tell me how can you say? So we saw, right? So for it to be group, we have to have these three properties, namely A, B, C. So clearly A is given, that is the associativity. This ABC is equal to ABC. A into B, C is equal to A into B into C. So that is there. What about the second, these two properties, B and C? How can we say from the second statement that those B and C are completely satisfied? Any intuition? I mean, how will you proceed with such statements?
We will equate AX is equal to YA.
Sorry.
AX is equal to YA.
Okay, AX is equal to YA. Okay, then. So when I'm writing this, AX is equal to B, what does this mean? That X is a variable here, right?
Yes, ma'am.
So X is a variable. So what it is saying that all for any given A and B, for any given,
There exists its inverse.
yeah, yeah, there exists is inverse. No, I mean, yeah, we can say that. But first of all, inverse to exist, we first need to have identity, right?
Yes, ma'am.
So how can we talk about identity using this property too?
If you take B
What
as
A and B will you choose in order to have this solution of this equation or this equation to be identity?
if you take B as A,
Yeah, exactly. So if B as A, then what I will have, A into some X is equal to B. This has a A has solution, and this Y into A also has solution. What does this mean? That there exists some E such that this solution, if we say that it is E, then A dot E is equal to A, and E dot A is again A. So this is what we get. So our first property is taken care of. And now we have seen that it has solution in G. This is also important. Okay, the identity must be inside G. So this E which we have got is actually inside G. So that's why the second property which we needed for G to be a group is satisfied. So and for it to be inverse, what choice of I can say B or A we can have? Hello.
if you take B as E, that I will take.
Yeah, exactly. So now that we have E inside our G, we can have that AX is equal to, if I consider, and again YA is equal to E, then this X and Y which we will get here will be namely the inverse of our element A in the group. So this will be a group.
Ma'am,
If you have any question, please stop and ask me
ma'am,
anytime. Yeah. Yes.
but in the group we need uniqueness of identity.
So uniqueness we can prove using this associativity. Okay. Uh, don't you think? I mean, okay. Suppose there exists some another e dash, then e dash dot e is equal to e. The basic proof which we prove used in normal group definition in to prove the uniqueness of identity, the same will follow here. Okay, suppose that is e dash and e are two identities, then e dash e is equal to e dash and e dash e is equal to e, and then ultimately we get this to be equal. That's how we normally prove, right? If something is identity, then this is true.
That's fine.
I hope I'm clear, right?
No, like in this first equation, ax equal to a, we have x is some x will be fine. What is the guarantee x equal to y? We choose.
Okay, so you are saying that if suppose that AE is equal to A and some E dash A is equal to A, in that
Yeah.
case, but then again we what we can say, mm, so for this to happen, what we can have is suppose let so we have in order to prove this we again have to go through this equation. So what we have that A dot E is equal to A, and now suppose E dot something we want it to be equal to A, right? And again we can consider this, and this X would give us the required solution, I guess. Just a second. Hello.
I think like a is equal to a, as you can get.
Mm-hmm.
Then you can write second e dash a is equal to a, e dash a, e dash
Okay, E dash A is equal to A.
and you can replace that a by ae, like right hand side of the e equals to ae.
AE. Okay.
E dash equal.
But that is not giving us E to be
Yeah,
equal to A, right?
that's what we
E
say.
dash.
Yeah.
So then you can do one thing, multiply by left inverse A inverse from both sides and then associative property. It will give E dash is equal to E.
You are saying E inverse of E dash?
No, inverse of A. You can multiply from left inverse of A from left
Okay.
side.
Okay, from left side. A
A
inverse.
inverse E prime A.
A inverse E prime A is equal to A inverse AE. That's what you are saying. And then you are saying that this E dash A is again our A.
No, associative property you can use left side. Then
Okay.
A inverse A will be identity.
Associativity means that ABC is equal to, I mean, the either it could be this or this. We can switch A and A inverse, right?
Yes, that's the same thing.
Okay, so which one you would like to choose? This one?
No,
or this
using
one?
associative property. Just we A, A inverse A E will come, na?
So this is anyway,
This is E. This is equal to E,
yes.
and left side will come E inverse. E prime. If we so E prime is equal to E is coming.
No, it need not be, right? What we have, E prime A is equal to A. So this is A inverse A. But again, this, if we consider A inverse A to be E prime, in that case, that will happen.
Yeah.
I mean,
Okay.
once, see, what I wanted to say is that these definitions, when we write that B and C, we only talk about the existence, right? We want elements to have such properties. And once we have elements, I mean, was any set which was satisfying this property. And using these properties, we have got the existence of this E and this B, which is namely A inverse in our case. And then the rest properties which we have, that which we use to prove E dash is equal to E in our normal sense of group theory, that we can anyway prove using the normal group definition. Because once we have the definition of this, I mean the existence of this identity and its inverse in the group, the rest is our routine thing. This was just to give the flavor that the existence of inverse and uh, additive identity, or let's say if multiplicative group, then multiplicative identity are just solution to these equations. I hope I'm clear. Hello?
Ma'am, can I say something?
Yeah, sure, sure.
Can you please take this down? Yeah.
Yeah.
Can you multiply A with both side where you have written A inverse E prime A,
Here again,
that
you
thing?
want me to multiply by A on the right?
Yeah. Both side.
A inverse?
On the left. Sorry.
Okay,
Yeah,
on
on
the
the left.
left by A.
Yeah. And that will be A
That
E.
this is what you are saying? Okay. Okay, this
Mm,
is
E inverse A. Oh no. That will not happen, I guess. Ma'am, please multiply it with A. The equation A inverse, you have to multiply with A and equals to AE. The
so
right
this
side will
is
be AE.
okay. So let us say our AX is equal to A was there, and YA is equal to A was there, right? And we were saying suppose the solution to this is E and this is E dash, and we need to prove E is equal to E dash, right? So what we have is AE is equal to A and E dash A is equal to A, right? And now,
Ma'am,
suppose,
actually, in a
yeah,
group, we have a cancellation law works, right?
but let us try to prove it using without using cancellation law. So now let's see, B belongs to G. Then again, this solution, these equations will have solution, right, for any given B. Then from this, what we have, AX is equal to B. What this will imply? Can somebody tell me?
X equals to A inverse B.
Now we have. So and then using, let us call this 1 and 2. Then what we can have, this E dash into this AX is equal to B, right?
Yes.
Okay. Then what this will give us, now associativity, if we use, then this will happen. Is this true? And what is this? This is again our A. X is equal to, and now on B I use E dash again. B is again, since E dash B is also true, then I will write it as E dash B. Then what I get, what, and now what was this AX? It is B is equal to E dash B. Okay. So now, for now, keep this. From AX is equal to B, what I got? B is equal to E dash B. And now let us start with this A is equal to B. This will imply what? YA dot E is equal to B dot E. And again using the same Y AE is equal to BE. Then this AE is again A, and this is BE. So B is equal to BE. So using this, what I got, that E dash B is equal to BE. Sorry, B is equal to BE, and B is equal to E dash B for any B in G. So this is true for any B in G. So in particular, this is true also for E, right? Hello.
Yes, ma'am.
Yeah. So this is true for B is equal to E if I take, then E is equal to E dash E, and E dash is equal to E dash E. So this will give me E dash is equal to E. And now is this clear? I mean, we had to make this true, that for any given element, we need to have this condition. I mean, this is exactly what we were doing. That this E dash and E which we got are solution to both of this. The B which we needed to choose were actually E itself. I hope this is not getting too complicated or you are lost in between. Hello.
Yes, ma'am. You can proceed.
Yes, ma'am, I got it.
Yeah. Okay. I mean, it was nothing. We just had to choose the B smartly. We already had a E dash is equal to E dash, and E is equal to E dash, and we just had to choose the B or our A smartly. So let us take another problem. Let us take these two statements, that every subgroup of a cyclic group is also cyclic, and every proper subgroup of an infinite cyclic group is infinite. Uh, what can you say about this truth statement? Are they true or false? true or false? I mean, can somebody guess? I mean,
First statement is true, ma'am.
okay. By the way, everybody knows what cyclic group is, right?
Yes, ma'am.
Yeah, okay. So, cyclic group is just group generated by a single element. And when I say a group generated by a single element, I mean that it is intersection of all the groups which contain that element. I hope everybody knows the definition of cyclic group. So, he said, like someone said that every subgroup is a cyclic subgroup, which is every subgroup of a cyclic group is cyclic, and which is true. I mean, can somebody say why this is true?
If we take an arbitrary subgroup of
Mm-hmm.
G group,
Okay, suppose our G is a group, and if we take arbitrary subgroup, then
G is generated by some element like some A power n.
mm-hmm. Let's say G is generated by A.
Generated.
Okay.
Then H contains there exists a n such that H will be some A power n. There exists element in H.
Okay.
In that, among the H elements, we will take the minimum power.
Yes, yes, and that minimum power is exists because of the well ordering principle. Okay, it's and so this is trivial statement. Can somebody tell me about this statement? I mean, every proper subgroup of an infinite cyclic group is infinite.
Ma'am, I think it is false.
Can you give me an example?
Z plus.
Okay, Z plus. Can you give me a proper subgroup of Z plus which is not infinite?
Set of 1 and minus 1 and 0.
This
No.
is under addition, right?
Sorry, ma'am.
Yeah. Here cyclic is important, okay? Can somebody?
Whether it is
Yeah.
true, I think so.
Yeah, this is true
Sorry, ma'am,
because
that is true.
as
True.
he said that if H is any subgroup of G, it is of the form A power n for some n in Z, or I can say just n plus or so on. So it is of this form, right? And if G is our infinite set, so if A power m is finite, if cardinality of this A power m is some k, so this implies what? A power m power k is identity. This makes our group G to be finite, which is not true because we have infinite thing here. So this is not true in case of cyclic finite cyclic set. I mean, in case of finite, we can't anyway have a subgroup which is infinite. That is different thing. But yeah, the cyclicness is very important. If I remove this cyclic, that every proper subgroup of an infinite group is infinite, then that need not be true. Can now somebody give me example where group is infinite and its proper subgroup is not infinite? Somebody just said something, and but can you just specify what
R
will be the
star
our
under
group?
multiplication is the group.
Which what under multiplication?
R star under multiplication.
Okay, R star under multiplication. Yes, in that case, what you said that the set -1 and 1, this will be the proper subgroup, which
Fine.
is not,
Yes.
yeah, which is not infinite. Okay, so I hope this question is clear that the cyclicness, I mean the of group being cyclic was important here. Please ask if there is any doubt in this question or I can move further. Okay.
Can you show the statement once more?
Yeah, definitely. I will clear this.
Okay, thank you, ma'am.
Yeah.
Ma'am, I have one doubt.
Yes.
What is mean by proper subgroup?
Okay, so proper subgroup means that it should be properly contained in our group G. So every proper subgroup means, because if I take G, for example, in this case, if R star, if H I consider R star in this case and this is R star, then this is always true, right? And proper subgroup is something that H is proper if H not equal to G and and H is called trivial. It's non-trivial means H is not equal to the singleton E. Non-trivial. Okay, so these two terms are really important when we talk about groups in general. I mean, sometimes if you miss these words proper and trivial in, I mean, reading the question, you might end up writing something wrong in the exam. So understand this properly. When I say proper, it means it should not be equal to G, and non-trivial means it should not be equal to the identity element itself. Okay?
Okay, ma'am.
Yeah. And somebody else was saying something. Hello? So let us, I guess this was enough for this question. So let us move to next question. So since we were talking about cyclic groups, can somebody tell me how to find the number of generators of a cyclic group of order 12? So do you know the formula for this? The number of
Phi of 12, Euler-Thomson function.
Yes. And so can you give me exactly how this will be? The number of generators. Euler, let's call this P. Then what will it be? How do you know how to calculate this?
Ma'am, phi of 3 into phi of 4.
Okay, then
Then 3 minus 1 into 4 minus 1.
4 minus 1.
No, sorry. 4 will be written as 2 square, I guess.
Okay,
Ma'am,
so
5 of 12 is 6.
sorry.
5 of 12 is 6.
Yes, it is 6. But you know, like this 12, we can write it as
3 into 4 and
yes, 3 into 4, that is 3 into 2 square. So we then this phi of 12 is this formula, if you know. 12 into this is 3, so 1 minus 1 by 3. And this is 1 minus 1 by 2. The index is, sorry, not the index, 1 by 2. So this will be 12 into what this is?
2 by 3
Into
half.
1 by 2. So what this is?
6.
Okay. So this is the formula you can take. For example, so this was 12. So even if you don't know exactly what the function is, so this is all
Actually,
set
answer
of,
is 4, right?
Sorry,
Answer is 4, right?
answer is
4.
yeah, exactly. That's what I was thinking. It should be 4. I mean, the GCD of just a second. Yes, it is 4. Yeah, GCD of A and D. I mean, in all the D's such that GCD of D and 12 is 1. Okay, so since this was small number, even if you don't know what exactly the formula is or anything, you can just look for elements which are co-prime to 12 and we can proceed. But in the exam, they might not ask such questions. Like what if they had said that order of G was 60, then how would you would have, like, if you go on checking whether each integer between 1 to 60 prime to 60 co-prime to 60 or not, then it would take like too much time, I guess, and you will just waste your time in the exam. So for in that case, just do this, that 60 can be written as 2 cube
12 into
3,
5, right?
yeah, 12 into 5, and then again it will be 12 into 5 means 2 square 3 and 5. Then in that case again 60 into 1 minus 1 by 2, 1 minus 1 by 3, and 1 minus 1 by 5. And what this will be? 60 into 1 into 2 into, I mean, again, in the denominator, we also have this. This 10 and again 2 and
16.
2. Is it
16 is the answer.
16, right? 16. Yeah. But you keep this formula in mind, okay? So this is phi of some A is equal to, just write its primary decomposition. Example, if P1 power A1, Pk power Ak, then it will be just A into, then phi of A will be A into 1 minus 1 by P1 up to 1 minus 1 by Pk. Okay, this is the formula. If you have never came across this formula, you can note this down. Okay, you just need to know the decomposition of this A into prime. I mean the unique factorization which we have for integers in general. Is that clear?
Yes, ma'am.
Okay. And now, just a second. Okay. So let us move with the next question. So if P is prime and G is non-abelian. Non-abelian everybody knows, right? So non-abelian means
Not commutative.
xy, yes, xy need not be equal to yx for some x and y in G. Okay, and we have this order of G is p cube. Then can we talk about the cardinality? Z of G, that is, this is center of G. It is all X in G such that Xg is equal to Gx for all G in G. Okay. So what will be the cardinality of Zg in this case? You have given that G is non-abelian and P is prime and order of G is P cube. Okay, so let us.
Possible.
Ma'am,
Yeah,
is it
exactly. Yeah. Say. Yeah, you were saying something, please.
Actually, center of the group is a subgroup of a group. So the
Yes.
order is divisor
Yes.
of P cube, right? So this
Yes.
initial idea.
So Zg is a subgroup of G. Then in our case, this is proper. So then
It is possible
possible cardinality will be
P or P square.
why not 1?
Yes.
Okay, P cube it's not. So in
Possible.
general, any for subgroup we have these three things. But in our case, our G is not abelian, so it is gone. So we have these three options. So what it will be among these three?
P will not be true because if the order of P is like Zg will be cyclic.
No. Order of G. Okay, ZG being cyclic is not a problem, right? I mean, what
Oh
is
yeah,
problem
yeah,
with
yeah.
ZG
G
being?
is non-abelian, not
Yeah,
Zg.
yeah, yeah, yeah. Exactly. ZG will always be abelian subgroup of G. I hope that is clear because it is set of all
Yeah, yeah.
elements which commutes. So yeah. Can somebody think of it? Mm, How to proceed? I mean, there are three possibilities for so on. Can somebody tell me? Is one possible in this case?
I think one is not possible
Yeah. Why?
since the quotient group
Exactly.
isomorphic
Mhm.
to G, so that G is non-abelian, so the quotient group is also non-abelian, so that's why.
Yes. So what he's saying that the index of ZG, if it is 1, I mean the if order of G is 1, then this will be P cube. Okay. And why you are saying that G is non-abelian is used here? I mean you are using some hidden result here, right?
Actually, first, fundamental theorem of group homomorphism, right?
Yeah.
Center of a group is normal, so that's why we can form a new group which is called a quotient group, so which is
Yes.
isomorphic to G, right?
Yes.
So
Mm-hmm.
G is non-abelian, so that's why the quotient group is non-abelian. This is the order of the quotient group is PQ. G also PQ.
Yeah. Okay. So I hope that is clear. So one will not be the case here. So there are two possibilities, P and P square. Can somebody tell me why it is not? I mean, which one you think will be?
Ma'am, can you repeat that?
ma'am P?
Yes, it will be P. Just a second. What?
Hello,
Yeah.
ma'am, can you repeat that? Why it is not being 1?
Why it need not be 1? Okay. So if that is the case, ZG is Just a second. By the way, G quotient ZG is always abelian. This people know? G quotient ZG is abelian. Hello?
Yes, ma'am.
Okay. So using that, if we have this, that G quotient ZG is P cube is non-abelian. So in that case, G quotient ZG will become abelian group, and which is not the case here.
Okay.
Okay. So we have now these two possibilities, that order of ZG now will either be P or P square. So which one it should be? So let us start. So if order of ZG is P square, then then what will be the possible quotient group? It will be G quotient ZG. And what this will be? It will have order then P.
P.
Yeah, then
And
G
this
by
will be
Z.
abelian.
This will be cyclic, right? And if G by
Yeah.
ZG is cyclic, then we know that then G becomes abelian. This is a result. If G by ZG is cyclic, then G is abelian. But in our case, G is not abelian. So that's the contradiction. So that's why the only possibility of ZG is P. Once we have this, then G by ZG becomes cyclic, and G by ZG cyclic implies G abelian. That's why this is not true, because G is given. This is contradiction, as G is not abelian. Hello?
Yes, ma'am.
Yes, sir. Is there any doubt here?
Can you prove the result?
Which result? If G by ZG is cyclic, then G is abelian this?
Yes.
I mean, okay, so we can prove this result right now, but what I would say, this is very, I mean, well-known result, and you can find this in any algebra book. If we prove this result right now, I think we won't be able to do much ahead. So,
Ma'am,
I mean, yeah,
Okay. Fine.
I
okay,
have a doubt that
yeah.
we can generalize that result, that if the order of a group is some p power n, then we can say
Yeah.
that the order of center of group is as p.
It need not be true for any p power n. Okay. Can we generalize this for any p power n? I mean, generalizing this for any p power n, I think would be difficult, because in this case, what if if it is, suppose our case was, if it is p power 4, then it will be order of then This will be G by mod cell G will be P square. And again, then this argument which we are doing in order to discard the fact that order of order of ZG can't be P square, this will not be true, because here once we have order of G by ZG cyclic P, then we can say that this P square. Okay, so let me write this. If my mod of G was P square, sorry, P power 4, in that case this G by ZG will be P square. And this thing which we were getting, that G by ZG is cyclic, and then we were getting contradiction that G is abelian, that we need not have. So we can't discard this option that ZG could be P square in that case. Are you understanding? I mean, there were three possibilities, right? We discarded one. Then we have now P cube is not possible, which we know. And then we discarded P square using this fact that order of G by ZG is P. Then that is giving us G by ZG to be cyclic. And that gives us that G to be abelian.
Okay, ma'am.
Okay. And but then it was giving that G is not abelian. So using this result, we could discard this P square from the possibility of order of it being order of ZG. But if it was not P here, if it was P square or anything, then we need not have this thing. Right? Because, for example, even if we take P is equal to 2, and then mod of ZG could be this P square, and then G by ZG could be, I mean, if it could be 4, then this need not be cyclic, right? There are many groups which are of order 4, which are neither cyclic even, and so on.
Yes.
Yeah. So, I mean, the Klein 4 group, that AB is equal to C and so on, that is one which is non-cyclic. And so I hope I'm making things clear here. Hello? I mean, this is only true for P cube, okay? Because we have to discard the possibilities of it being P square and so on. So it has to be.
Then we can make a remark like this, like the group is of order G, P power n, non-abelian.
Is P power n, G non-abelian.
Then we cannot have a center of G of order P power n minus.
Center of G, yeah, this
Will not be
is
order of
really
P power.
true. Yeah, using this, because once we have P n minus 1, then it becomes P, and yes, then ZG, you are saying cannot be equal to P power n minus 1, right? This is what you are saying.
Yeah.
Yes. And this you can look into any book. I mean, you will be able to find this, I guess. Yeah. If you are not following this, I mean, you can. I mean, if you see this proof and not able to understand, then you can just contact me if you want. Okay. But I think we should move ahead to our next question. Is it okay?
Yeah, ma'am.
Yes, ma'am.
Okay. Yeah, so we already saw something related to cosets in order to prove things. So let us move to next question. Maybe this is question 5. So what I have, if HA not equal to HB, then this implies that AH is not equal to BH. Then what can we say about the subgroup H of G? I mean, whether it is normal or it is quotient, it is cyclic, and it is group. That means that they are saying H is equal to, I mean, this is MCQ type question. So
Ma'am, here group means the group itself.
yes, H is equal to
G.
G, maybe, yeah.
Okay.
But this is MCQ, so let us start. How?
So
What
option
is
A
it?
and C,
Option
which is
A can be, it is not normal.
Can you give me an argument why it is not normal?
Ma'am, for normal, the right coset and left coset should be equal.
Right. So right coset and left coset, you mean this, right?
Yeah.
Yeah, but here what they are saying is that HA is not. So if I have A and B in G, then what they are saying is that HA not equal to HB implies that AH not equal to BH. They are saying something different. They are not saying that AH not equal to BH. This is not what they are saying. They are saying if I have some coset such that HA not equal to HB, then this implies, so if the right cosets are not equal, then left cosets are not equal. That's what they are saying.
Oh,
They
okay,
are
ma'am.
not saying the left cosets and right cosets are not equal. Okay, they are. So how to proceed? Yeah.
Can we do
Sorry.
from the given HA not from the given statement we can write like
Yes.
contrapositively we can write
Mm-hmm. AS is equal to BH
BH
implies
implies
HA is equal to HB.
yeah,
And what this prove is that
AH equal to
A inverse B belongs to
And
H implies AB inverse belongs to H. Okay, this is what we have. Okay, from given condition can be reformulate to this, that if H is a subgroup such that A inverse B belongs to H implies AB inverse belongs to H. Okay, so what to do now with this? So our first option is normal, right? So let us try to see whether it's normal or not. Okay. So in order to prove that G is normal, what we need to prove that H G inverse belongs to H, or G inverse HG belongs to H for all H in H and G in G, right? Oh. So let us take, so if H in H, then what this imply that H inverse is in H, right? H is subgroup.
yes, ma'am.
Okay. Then after this, what I can write is that, and let G be anything. Let G be in G. Then for this G, I can write this as G inverse belongs to H, right? This is true. This is just identity. So H inverse into identity belongs here.
Yes.
Okay. And then using associativity of the subgroup or group, I can write this. And what we have proved that if A inverse B. If A inverse B belongs to H, then AB inverse belongs to H. So this is, if I take this to be our A, this B, then what this imply that this H inverse G inverse G inverse no, inverse yes, this belongs to H. Okay, so G inverse, I mean here it was B, so we got B inverse, and here it was A inverse, so we got A. So it is like inverse of both the elements. So this more or less we can say that if AB belongs to H implies A inverse B inverse belongs to H. Okay, this is what this statement is actually. I hope this is clear. And then what this is? It is G inverse H, G belongs to H. And here H and G were any, so H was in H and G was in G, and they were arbitrary. So, and this is true for any given G and H. So we can say that H is normal, right? Is this clear?
Yes, ma'am.
So we just had to use this property, and this actually translates to this, that if AB belongs to H, then A inverse B inverse belongs to H. That's what this means. That's what I used here. Is this okay?
Ma'am,
Or
can you explain above AH equal to BH implies H equal to HP? From that you write this A inverse B belongs to H. How do you write?
this from this to this?
Yeah, yes, ma'am.
This is definition of quotients, right? AH is equal to BH implies B inverse A belongs to H, or A inverse B belongs to H. This is definition of quotient,
Okay.
right? I mean, or and this is exactly what I wrote. For this statement, I wrote this. So I'm taking A inverse here. And for this, I'm taking B inverse here.
Okay.
Okay. I hope this is clear, right? This is basic definition of quotients. I mean, that's how elements and cosets are related to each other as per the representation of a coset.
Ma'am, that means H is not normal, right?
H is normal because we got GH G inverse in H for any given H and G.
No, ma'am, you have taken H equals to BH in the first, then you prove it.
Where
But the
I prove?
question.
Where? No, here I am taking contrapositive. I am taking A
Oh, yeah,
normal.
yeah, yeah. Okay, okay, okay. I'm
P
sorry. I'm
implies
sorry.
Q, then negation Q implies negation P.
Yeah, yeah, yeah,
So,
yeah.
okay, contrapositive.
Yes, yes, yes.
Okay. So, next question, I think it was number 6. Let's say. I hope there is no more problem. Okay, this was MCQ. So, and we proved that it is normal. So, we don't care about the rest of the options here for now. Okay. So, let me say H1 and H2 be normal subgroups. And then G by H1 is G by H2. Then what can we say? And we have this G by H1 is equal to G by H2. Then what can we say about H1 and H2? Whether H1 is equal to H2 or H1 is subgroup of H2, or let us say third is H1 H2 subgroup of H1, or 3 H1 not equal to H2. Okay, I mean, what is your guess from this? If the quotients of two groups is same, then what can we, two normal subgroup is same, then what can we say about those subgroups or those normal subgroups? Okay, so what your intuition says, at least. I mean, looking that they are equal. So what is your guess, initial guess? Suppose you are in exam and you have to solve this.
I'm actually, our initial institution says first option is right, but it is not generally true for non-abelian or non-cyclic groups, right?
It is not true for
Non-abelian groups or non-cyclic groups.
why it is not true for non-abelian groups?
Suppose it is a group of infinite order. I'm
Okay.
taking it as a cyclic.
Mm-hmm.
Oh, sorry. We are not going to take a cyclic.
Mm-hmm. Okay, so let us try to. Okay, so for some cases you could see that it is equal, right?
Yeah,
So
yes.
let us try to. So this is MCQ. So let us try to generalize it and let's try to prove this that it will be equal. So first of all, we have that. So what is this G by H1? This is this is group of this form, right? Where A belongs to G. Set of all cosets, and then we have the group actions and so on going on. Just a second. Yeah. So let us try to prove this. So we have this thing. So this implies this H1 as a coset. I mean this EH1, which is H1. This belongs to this G by H1, right? I mean this coset, the set of cosets or this quotient group.
Yes.
I mean this as an element belong to this set.
Yes.
But again, this is equal to G by H2. This is what we are given. So this means H1 belongs to G by H2, right? So, and what this means that H1 is actually, I mean, and this set is again some AH2 where A is in G. So if H1 belongs to this set or this quotient group, so what this means that H1 is some coset of H2. So let us say it is some AH2 or this is true, right? I mean, H1 belongs to this implies this thing. This much is clear. At least let me know that this much is clear.
Yes, ma'am.
Okay.
Yes, ma'am.
So what we know that if two cosets are equal, then if If it has to be some, so if H1 is some coset of H2, then they are either equal or they are disjoint. H1 is equal to some AH2. And from this, how to proceed is, so what the intuition is that two cosets of any subgroup are either disjoint or identical.
Ma'am, can you write same for H2, like H2 equals to AH1?
You mean, okay, you are saying H1 is equal to AH2, and then this will be B, H1 is equal to H2.
H2, yeah.
Okay, and using this, what can we say? So understand that E is in H2, right? E is in H1. E is in H1. So this implies E is also in AH2. Okay, so this implies that we somehow need to prove that this AH2 is actually my H2. Yes, we are there. So understand that as we said that this H1 is some AH2, right? And we have that E belongs to H1 since E is an identity. So this implies this E is also in AH2. But note that this E is also in H2. And we know that two cosets are either equal or disjoint. So what this imply? That since E belongs to this, either they are equal or disjoint. So but E belongs to both AH2 and H2. So this implies that this AH2 is nothing but H2. And what we have from here is that H1 is H2. Is this clear?
Ma'am, can you repeat,
Yeah.
please?
So let us start. Okay. From so GH1 is just set of cosets or quotient group, and we are given that so this H1 or this EH1 is in is element of this G quotient H1, but it is equal to G quotient H2 or quotient of H2. So H1 is again element of G by H2. Look at this as a set, okay? And this AH1, BH2s or A1H1, B1H2s as elements here. So, and this H1 is element here in G mod H1, that is this EH1 it is. And but G mod H1 is equal to G mod H2, so this H1 is in G mod H2. Okay, so and what is G mod H2? It is some it is set of all quotients of H2. So what this means that H1 is some quotient of H2, because elements of this set G mod H2 is of this form. So, and we know that this identity element is in H1 because H1 was our subgroup. So by this equality, we have identity element inside H2. So this is as per what we have. But also note that this EH2, that is EH2, is also coset, and it also part of this, also element of this G mod H2. And we know this fact, the cosets actually partition the group, right? So either two cosets are equal or they are disjoint. But here we have in these two cosets, EH2 and AH2, this element E belongs here and element E belongs here. So this implies by this property that two cosets are either disjoint or equal. EH is equal to EH2 is equal to AH2. And what is this EH2? It is H2 is equal to AH2. And what was this? This was our H1. So this is how we got that H1 is equal to H2. We are using this property. Let me highlight it. That cosets are either equal or disjoint. Oh my god. Two cosets are either equal or they are disjoint. Is this okay? Because there is an element which belongs to both the cosets become equal.
Yes, ma'am. I got it.
And so I'll move to next question. Just a second. Yes. This is really a trivial question. So I think it is 7. So let G be non-abelian group, and F be mapped from G to G such that f of x is equal to x inverse for all x in G. So can this F be a group homomorphism? You know what group homomorphism is, right? F from G to G is group homomorphism if f of AB is equal to f of A, f of B.
It will not be
And
a group homomorphism
yes, can you tell me why?
because f of AB equals to AB whole inverse and it is not abelian. That's why we are writing B inverse A inverse.
Mm-hmm.
And that means f of B into f of A.
Yes. Yes, this non-abelian property of this group is playing the role here because we can't simply write it as f of this need not be true. So that's why this is not a group homomorphism. And this is also one question related to can we give the number of group homomorphisms from this Z plus to Q star. So this Q star is under multiplication and Z is under addition, such that f of 2 is, so if f is this, 1 by 3. So the number of group homomorphism, or I would say, let me write number of group homomorphisms is 1 by 3.
Zero, I think.
Yes, it is 0. I mean 0. Can we say why such function does not exist, or why such group homomorphism does not?
We can use
Yeah.
properties of group homomorphism. That is, f of 2 can be written as f of 1 plus 1.
Exactly. Or I would say f of 1. This will be f of 1 square, right? So
Yes.
we are now in Q star. This everything is happening in Q star.
Yes.
Yes. And I want this to be 1 by 3 square. So I want f of 2 to be 1 by 3 square. Sorry. 1 by 3 to be square of f of 1. So this implies f of 1 to be 1 by root 3. But this is not rational or does not belong to Q star. So we can't have such group homomorphism.
Ma'am,
Ma'am,
why 1 by root 3 came? How
It's
the
not.
1 by root 3 came?
F of 1 square is 1 by 3. So f of 1 could be like, okay, plus or minus 1 by 3. But yeah, from this I am getting that f of 1 is equal to root of 1 by 3. 1 by.
Okay, ma'am.
Okay.
ma'am, if we take irrational numbers without taking rational numbers, then can we find out the numbers of group homomorphisms?
Okay, then it will be infinite, I guess, in that case, because Z is
Infinite for
cyclic. Yeah, it is cyclic group. So if we set any f of a to be f of 1 to be some, for example, nice number, let's say 2, then everything would follow. Or some, I mean, in this case, f of 1, if I defined, suppose if this was 4 instead of 3, then f of 1 we can define it to be 1 by 4. Then we can just have f of 2 to be 1 by 4 into 1 by 4, 1 by 16, and so on. So in case of cyclic group, the entire group homomorphism can be defined, or I would say can be obtained using just the generator of that group. I mean, the generator of the domain. The only thing we need to take care here is that the identity here goes to identity there. Right?
Yes, ma'am.
Yeah. F of 1 to be the, yeah, yes.
Can you give, in general, how many group homomorphism from Z to Q? I mean Q star. Not restricted by this kind of condition.
Yeah, okay. And I would say there are infinitely many. because we can always choose, for example, this is one group homomorphism. And here f of minus 1, we can define it to be 4. Right? Then so that f of 1 minus 1 will be 1 by 4 into 4. Then this will be my 1 and here it is f of 0. So identity here is going to identity here. So in that case, there will be infinitely many such functions would exist. We
Okay.
just have to take care of these squares or and in some cases, I mean, also cubes we can see, because if here it was 1 by f of 1 by 2 was 1 by 3. Similarly, we can take f of 1 by 4 is equal to 1 by 3. This will also be not true, because this again f of 2 into f of 2 will give me 1 by 3. Then again square root of f of 2 need not exist. So this algebraic or I can say polynomial oriented things where x power n is equal to some k, we have to take care of such things. But apart from that, I think there are infinitely many which we can happily define. Without such restriction, there are infinitely many.
Okay.
Yeah. I mean, shall I again proceed with, or I mean, okay, just a second. So we still have. So I will now quickly go to group actions, because there are also just a second, let me add few pages.
Can you explain group actions in detail, please?
Okay. Just a second. So let me start with the definition of group action. So let X be a set and G be a group. Then an action of G on X is a map, let's say phi, from G cross X to X. So it is like G is acting on X and giving us again an element from X, which satisfies certain conditions, satisfying that phi of EX, I mean E comma X, is X. That is, when identity element acts on X, is again gives us X for any X. And second condition is that this phi of G comma PHX is phi of GH comma X for all X in X and G comma H in G. So in short, if this phi and all, if it is getting confusing or doesn't look good, then we said that G is group action if Gx is X for all G in G, sorry, Ex is X for all X in X. And second property is that G acting on Hx is similar to Gx acting on X for all X in X and Gh in G. I hope the definition is clear.
Yes, ma'am, but can you explain with an example?
Okay, so let us try to solve a question, and in between I will explain you like how the group action is defined or so on. Okay, I mean we will be defining a group action in order to solve that question, so it will also clear most of the doubts in the process. So consider this. I mean, it's okay, right?
Yes, okay,
Yeah.
ma'am.
Yeah.
Yes, ma'am.
Yeah. So I'm writing this here. So true or can you? So Sn everybody knows, right? Sn, the set of all symmetric. I mean the set of all permutations on n objects.
Yes, ma'am.
Sigma belongs to Sn, so that sigma is permutation. Okay, so question is that summation of sigma belongs to Sn, number of one cycles in sigma is what? So every sigma in Sn has cyclic representation, that everybody knows. So how sigma looks like? It is like, so since we are, so let us take n to be 4. So it is like 1, 2, 3, 4. And it is sigma 1, sigma 2, sigma 3, sigma 4. So this is actually bijection, okay? Sigma you can consider as a bijective map from set of all n variables to, or n numbers to n numbers. So this is just bijection, set bijection function. So this will be something. So this sigma, we can write it in the cycle form. So for example, if I take particular sigma to be 1, 2, 3, 4, and let me write it as 1, 3, 4, 2. Then I can write it as cycle that 1 is going to 1. Okay. And then 2,
2, 3,
okay.
4.
2, 3, 4. Yes, 4 going to 2, 2 going to 3, and 3 going to 4. Okay. So this is the cyclic expression for any given sigma. Okay, this is we can have. So what they are saying is we are taking summation over number of one cycles in sigma. Okay, so what is it? So let us take Sn to be n to be 3, and let us understand what this question is. Let me copy this. Okay, and it says number of one cycles in sigma. So all the elements of sigma, how they are? So first is 1, 2, 3, 4. That is element which fixes every element. And then this element, oh sorry, not n is equal to 3. Then 1 going to 2, 3 fixed. 1 going to 3, 2 fixed. 1 fixed, 2 going to 3. And what are, so these are 4 elements, and rest is this cycle. 1 going to 2 going to 3, and then this, right? And what they are asking is number of one cycles. So number of one cycles means these are one cycles, okay? The fixed points. I mean the one which is not moving are one cycle. So for example, here one number of one cycles is 3. Here number of one cycles is 1. Here it is 1. Here again it is 1. Here it is 0, 0. Okay. So what is this? It is 6 in this case.
Ma'am, can you explain once more time?
Okay. So what is that you couldn't get? I mean, if the question is specific, I can proceed accordingly.
Ma'am, I don't understand why you are written 3 in that 1, 2, 3 cycle.
Where 3?
In number of 1 cycles.
For
That's
the
why.
1 cycles. I mean, we are counting the number of 1 cycle. So this is sigma 1, this is sigma 2, this is sigma 3, sigma 4, sigma 5, and sigma 6, right? So this is our identity where everything is fixed. So we are writing it as cycle 1, 2, and 3. So number of 1 cycle. So this is, so okay, this is my 1 cycle. This is my 3 cycle. On 2 cycles has nothing but transposition. It is just naming.
Okay, ma'am, I got it.
And 4 cycle will be 1, 2, 3, 4. This is just 4 cycle. Okay.
Okay,
So
okay.
we are like writing it in the form of cycle, and it is just cardinality of that cycle. So we want to find the this. They are first saying the number of 1 cycles in sigma, then they are taking sum over all the sigmas. So here for this sigma 1, the number of 1 cycles is 3. Number of 1 cycle here is 1. Here is, I mean, let me. So this is 1, 1, 1. So it's 3. Here these are the only 1 cycles in this 3. And here there is no 1 cycle, right? There are, and not even 2 cycles. We only have 3 cycles here.
Okay, ma'am.
Okay, so this is what we want to find. Okay.
Okay.
So in order to find this, these are also like fixed elements in our permutation, right? So let us consider now this set. So let G to be our Sn, okay, because we are summing over Sn, and let X be this set 1, 2 up to N. Okay, and now we define this G action on X, that G cross X going to X, that so it is some function again. So if sigma is in G and if K belongs to X, then this sigma K is K itself. K sigma into K is not K, it's sigma K. So to be precise, so if I take N to be 3, then G is my S3 and X is 1, 2, 3. And then this G cross X to X is that if I take sigma 1 in G, so sigma 1 and X is some element, right? From 1 to 3. So sigma 1 of 1 will be, sigma 1 was our this fixed cycle. 1, 2, 3. So sigma 1 of 1 will be 1. Sigma 1 of 2 will be 2. Sigma 1 of 3 will be 3. Okay. And if I take sigma 2, then sigma 2 of 1 will be, sigma 2 was this 1, 2, 3. Sigma 2 is 1, 2, 3. So what sigma 1 is? It is 2, right? Because sigma 2 of sigma 2 of 1 is 2. Sigma 2 of 2 is 1 and sigma 2 of 3 is 3. So this is how the action is defined. Is there any doubt in how this action is defined here?
Ma'am, please repeat it.
Okay.
How you're defining it, please repeat it.
Okay. So what we have is G is defined, G is acting on this set. Okay. So how this G is acting on this set? So every element of G. So what are elements of G here? The elements of G are nothing but the permutations. and it is now acting on the elements of X. So elements of X are what? These integers I. Then how it is defined? That sigma of I, sigma acting on X, I mean the element of I, is what? Sigma of I. This is how I am defining it. When we say that G is acting on this X, doesn't mean that every element is acting on entire set. It is acting on, so for example, if we take A cross Z cross Z acting on Z, so how we can define the action? That A comma B going to A plus B, maybe. So this is some element of B, right? Z here. Is there any doubt? I mean, what is that you are not able to understand? I mean, the group action itself is the problem, like how it is defined and so on.
No, ma'am. How you're writing sigma 1 3 equals to 3? That's the problem.
Okay, so sigma 1 is a cycle. You okay? What is this? So when we write sigma, what is sigma? Sigma is 1, 2, up to k. And what is this sigma 1? Sigma 2, sigma k, right? In our case, what was sigma 1? It was 1, 2, 3, 1, 2, 3. So what this is? 1, 2, 3, sigma 1, sigma 2, sigma 3. Okay? Sigma 2 was, what was sigma 2? It was cycle 1, 2, 3. So what it was? 1, 2, 3, 2, 1, 3. So what this is? 1, 2, 3, sigma 1, sorry, sigma, this was 1, this sigma 2, 1, sigma 2, 2, sigma 2, 3. Sigma 2 of I is how the sigma, where this I is going in the cycle in the permutation sigma 2.
Okay, ma'am. I got it. I got it.
Okay, so
Yeah,
sigma
yeah, yeah.
I, okay, so sigma I of some k is where that k is going in that sigma, because that's why I have written that G is acting on this entire set. Okay, I hope that's not now it's clear, because this,
Yes, ma'am. Yes, ma'am.
okay, is it clear to everyone?
Yes, ma'am.
Okay, okay. So now do you know orbits of a group actions, right? So orbit of X is Gx for all G in G. That is, what are all the values X is taking under the action of G. Okay, so for example, if I want to talk about the orbit of 1 here, then what it is, that sigma, what is sigma of 1, where sigma belongs to all the essence. So what are all the possible values sigma 1 is taking? So so we can see here sigma 1 is 1, here sigma 2 of 1 is 2, here sigma 2 of 1 is 3. So the orbit of this one is entire 1, 2, 3. Okay, is the
Ma'am, if the
definition?
sigma is in is 3, right? then we can say the orbit of 1 is 1, 2, 3.
Sorry,
If the sigma belongs to S3, then we can say
yeah,
it is the
yeah. S3. I'm talking about particular example instance. Yeah, it's in S3. And in general, the orbit of 1 in, as she said, that sigma 1, sigma belong to Sn will be entire 1 to n in that case. Because if I am taking Sn, then my x to be 1 to n. That's what we are taking. I hope the action is clear so far, and the number of the orbit is clear. Is there any doubt, like what is orbit and how the action is defined here? If you have any doubt, please.
Can you repeat what is the action here?
Okay. So G is acting on, so let me write it explicitly. S3 or Sn is acting on set of all the 1 to n's. Okay. And how the action is defined? That any sigma belongs to Sn, and for any k belong to 1 to n, this sigma acting on, or let me call it map. This sigma of p comma this k is sigma of k. What the sigma of k means? Sigma is some permutation, right, of n variables. So this sigma of k is where this kth element in this permutation goes. Okay?
Okay, ma'am.
Okay. So this is our group action. This is the group action. Is this okay? Okay. Now
Yes.
what is okay, let me just repeat now the orbit of any element. So let us in particular understand orbit of 1 in this case is what? How all these sigmas are acting on 1, where sigma runs over all. So it is like looking at all possible values. How this group acts on this element 1, or what are all the values 1 takes. 1 means this second component, if I take k to be 1, how this group G acts on this element 1 in this entire process. So if we take identity, okay, 1 going to 1, 2 going to 2, 3 going to 2, n going to n. In that group, in that permutation sigma, 1 will go to 1, right? I can also have a permutation where 1 is going to 2 and 2 going to 1. In that case, sigma of 1 will be 2. So 2 is also possible. And I can take permutation with all such possibilities, right? I can send 1 to any integer, any number from 1 to n in sigma. The permutation is all possible permutations, okay?
Okay.
So it is
for
entire
this,
set. Yeah.
for the different sigma, we can find different orbits. Am I right?
Exactly. Yes.
Okay.
For
Okay, ma'am.
different elements, we can find different orbits. Each sigma is sending your element 1 to, so orbits are defined for x in x, orbit of x. So G is acting on x, then orbit of, just a second. Mm. Oh, yeah. Sorry for that. Yeah, orbit of X. You were asking something, or so orbit of X is all the possible values X would take under the action of group G. Is this okay?
Yes, ma'am.
Okay.
For all G, right, ma'am?
Yes, for all G. For all G. Yes, for all G.
We can
So
like
that's how it is getting the entire set, because if I choose all the permutations, for example, consider in this set only, in this set, if I want to find sigma of 1, okay, sigma 1, orbit of 1, or let me write it as orbit of 1. So it is like how this sigma is taking, where the sigma is taking 1 in for all the sigmas, okay, where so sigma, when sigma is sigma 1, then 1 is going to 1. When sigma is sigma 2, 1 is going to 2. Okay. So this is my sigma 2 of 1. This is my sigma 2 of 1. Understanding? And in this third permutation, we are getting all this. And these are all the possible choices. Okay. Is this clear how the orbit is? Like I have to check for all the possible values X is taking under the group's action. So G runs and X is fixed. So we can look at it as G is running and X is fixed. Is there, I mean, is it clear now what is order?
Ma'am,
Sorry, orbit.
can
Yeah.
you find the orbit of 2?
Yes, we can find orbit of 2. So orbit of 2 is what? Where this sigma is sending to, where sigma is in Sn. So let me write it here. Okay. So here sigma in the first case, in first cycle, 2 is going where? If this is my sigma, then 2 is going where? In sigma 1?
2.
2, right? And here in sigma 2, where is it going?
1.
1. And in sigma 3, where is it going?
2.
2 itself. So we already have 2 here. In the sigma 4, where is it going? 2 is
3.
going to
3.
3. And then rest is okay, because this is my entire set which I was looking for. This was my S3. So this is orbit of 2.
So similarly, orbit of 3 is
Again, it will be
all
similarly.
the elements of X.
Okay, let me write. Okay, here 3 is going to 3. Similarly, for sigma 2, 3 is going to 3. So we don't care. 3 is now going to 1. In sigma 4, 3 is going to 2. Okay. So in this particular group action, the orbits are all equal for every element, but this need not be the case in general. Okay. We have now a bit nice group here, but this need not be the case. We can have orbits completely disjoint. Okay.
Okay, this particular action, the orbits of all the elements are like
Is
this.
it? Yes,
For the
it is
different
same.
action, we can find different orbit. Maybe
Different orbits.
it may
Yes.
be disjoint or something.
Yes, it will be disjoint.
Ma'am, actually, what are the purpose we are doing this group actions?
So actually what we want to do is, we want to find this number of 1 cycles in sigma, where sigma runs over Sn. And such questions are actually asked in JAM and NET, or in JAM mostly in those numerical type questions. So we are discussing this, that what is the number of 1 cycles in sigma, and then we are taking summation of all the essence. And this was we tried it for 3 and we are getting 1. Okay, so this is 1 cycle. So here what we can see, this 1 cycles in the sigma are exactly equal to what I was about to go to, is fixed or stabilizers of elements.
Can you state
Okay.
this problem like 2 cycles?
For 2 cycles.
Yes.
So you mean S2?
S3,
Okay.
the same group.
Okay, you want to understand this for that summation sigma belongs to Sn, number of 2 cycles. This is what you are asking? So
Yes.
what? Yeah, so again we have this, right? So here number of 2 cycles is 0. Here number of 2 cycles is 2. Sorry, 1. Here number of 2 cycles means the cardinality of each cycle. Here again it is 1. Here again it is 1. It is 0. So what it is?
3.
3 in this case. Okay, so this was, and if it was 3 cycles, then it would be for 2 cycles, let me say 3 cycle, it will be 1 1, rest is, I will write big 0 here, 2. Okay, so this question, and I will tell you this is nothing but n factorial actually. And I was about to give you the proof for this. I mean, how it is actually. Let me just delete this. I mean, you got the idea, like what exactly this is doing, right? So we are trying to find all the number of 1 cycles and taking sum over it. And we want to prove that that number of orbits is actually equal to. So there is something called as orbit counting theorem. Okay. So it says that the number of orbits is actually equal to 1 by order of G into summation sigma belongs to G x power sigma. Okay, so I will explain everything. So what is this x power sigma is? It is set of all A's in G, okay, all K in X such that sigma of K is K. So earlier what we had, order of X. Here it was, everything was running over G, right? What now we are doing here is, here sigma is fixed and we are checking, we are considering all the elements which are fixed under the order of this sigma. For example, if my sigma 1 was 1, 2, 3, then x of sigma is what? K belongs to X such that sigma 1 of K is K, right? So what are all the elements where sigma K is K? It is all 1, 2 and 3, right? Because sigma 1 is 1, sigma 2 is also 2, sigma 3 is also 3. Let me write sigma 2 is what? K in X such that sigma 2 of X is X. What was my sigma 2? It was 1, 2 and 3. So what are all the elements which are fixed or which are not changing under the action of sigma 2 is
3.
3. Exactly. And now let's write this sigma, I think it was 6 or yeah, sigma 6 maybe. Yeah. Sigma 6 was what? 1, 3, 2. Okay, this is sigma 6. So K belongs to X such that sigma 1, sigma 6 of K is K. And then what it will be?
Empty set.
Exactly, empty set. Okay. So you got the hold of what the stabilizer is, right? Under the action, we are just looking at the elements which are not moving at all. Okay. So what this order counting, orbit counting theorem is, as I said earlier, that these orbits actually partition this set X. In our case, the entire orbit was the same, right? For any given element, orbit of 1 was equal to orbit of 2 is equal to orbit of 3, right? But this need not be equal in general. Then we have this, that number of orbits is actually equal to 1 by mod g summation of x power sigma. This x power sigma is this stabilizer. So summation runs over all these stabilizers or such sets which
Whether
are
the
fixed.
definition is correct.
Sorry, sir. Sorry.
No, whether definition stabilizer is a subset of G, right? Set of
No,
all
no, 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 no. Stabilizer is again a subset of X.
X.
Yes. Or orbits are also subset of X. Stabilizers.
A set of all sigma belongs to G such that sigma K equal to K. I think so. I'm sure.
No, I think it is correct.
Okay.
For this sigma, we are checking what are all the elements which are fixed. Okay, now that you have said, let me just check it.
Excuse me, Siddhi.
Yes, sir. Yes, sir.
Yeah, we are running out of time almost.
Yes, sir. I'm just about to say just last 2 minutes.
Okay.
Yeah.
No problem.
It's correct. It's a subset of X itself and not a subset of G. Yeah. So what I wanted to say that this number of 1 cycles are corresponding to nothing but this So what we have is here that the fixed points in sigma, okay, fixed point in sigma, that is this xg. So observe that here x sigma 6 was empty set, right? Let us go here again and now see that cardinality, just a second, cardinality of x power sigma. So here number of elements fixed are 3.
3.
Here fixed are
1.
1. Here 1,
1.
1, 0 and 0. Okay. So this number of 1 cycles here are exactly equal to the number of stabilizers under this sigma. Right? They are in 1-to-1 correspondence. And this is also true for 2 cycles if I take. Sorry, not the 2 cycles, but yeah, for 1 cycles it is exactly the fixers or the stabilizers of these elements. So then by this theorem exactly we get that number of orbits is equal to 1 by mod G is equal into summation x power sigma. Sigma runs over Sn, right? In our case, it is in our case it is G is Sn, X is this set 1 to n, and action is what we have defined. And we saw that number of orbits is 1. There is only one orbit, right? For all the elements, the orbit is same, 1, 2, 3. So this is the only orbit which we have. Is there any doubt in this? When we checked for all the elements, this is the only orbit which we have.
Yes.
So number of orbits is 1 in this case. Right? How many orbits are there? Only one orbit. 1, 2, 3. For any given element,
Yes.
this is the only orbit which we have. So there is no other orbit. So only one orbit, and 1 by mod G is what? Or mod G is what? Sn in this case. So it is n factorial, and summation sigma belongs to Sn is x power sigma. But this is what we saw is, so if I switch, this is n factorial, summation sigma belongs to Sn, and this is what? Number of all 1 cycles. So this is what we were looking for. I hope this is clear. The 1 cycles were in 1-to-1 correspondence with this sigma. And why this group action was needed is because of this. So we could use this formula or this theorem, which is called orbit counting theorem or counting theorem. So using this, we could able to find this, because in any given, because see, from intuition, for number of S3 case, we had this 6. This 3 was 3 factorial, but this 3 could this 6 could also be 3 into 2, right? And you won't be checking things for S4, right? We have 24 elements there. Okay, so
Ma'am, this is true for number of 1 cycles, right?
yes. This is true only
Not
for
for 2
number of 1,
cycles.
not for 2 cycles.
Okay, then n factorial is not for 2 cycles.
No. This is only for 1 cycles. Only
Okay,
for
ma'am.
1 cycles. Only for 1 cycles. Yeah. 2 cycles it is not. We saw somewhere, right? It was different. In between, we made a table where we were trying to see. Okay, it's gone maybe. So I guess that's it. Is there any doubt how? I mean, I hope I made it clear how the action is acting, what orbit is, and what is stabilizer. Okay, and if just a remark that if anybody is going for any interviews where you say that, okay, group theory is my favorite subject and you can ask me questions, then group action is the one which mostly people go for. Okay, so yeah, I guess that's it, what I wanted to say for today.
Okay, ma'am.
Yeah, if you have any doubt so far, I would, whatever doubt you had in between, please ask.
Ma'am, in general, I was saying that in general, how can we find the number of 2 cycles or 3 cycles if there is any question about it? Not for 1 cycles.
Okay, I understood. Instead of 1 cycle, what about 2 cycles and so on? That's what you are asking. So in this case, for 2 cycle, we got it to be 3. Okay, and if I had sigma 4, in that case, number of 2 cycles will be 1, 2, 1, 3, and so on. It will be 4 in that case. In 5, it will be 2, 2. It will be more than, I guess, it need not have such good formula maybe, but yeah, one can look into it. Right now I don't know what it would be.
Ma'am, can we do the partition of numbers to find the number of elements of any cycle or a fixed order?
You can partition in what sense?
Ma'am, particularly for an example, if we take S3, we can
Mhm.
partition that is 1 plus 1 plus 1, then 1 plus 2 and 3. And from there we can find the number of elements of order 2, 3, and like that.
Yeah, I mean, there are many ways to do the things, and if we can, I mean, it does not sound wrong completely. I mean, we can proceed and we can see if we can find, we can obtain the answer. But yeah, I don't know. I mean, such a clear formula will be there for 2 cycles or 3 cycles. But just a second. Yeah, but for example, if I am in Sn and I'm talking about n minus 1 cycles, uh, n cycles, then in that case it will be n minus 1. This we know, right? There are n minus 1 n cycles in Sn.
Yes, ma'am.
Yeah, so for such special cases, for example, 1 and n cycles we can make, but for this in particular 2 cycles and so on, it's a bit difficult. It is similar to what we saw in this 1p, p square and p cube case. So, like when we have for particular number, things are nice, but when we go to look for arbitrary things did not look as good as we want them to look.
Okay, ma'am.
Yeah.
Yes, sir. It is
Yeah,
very
yes.
nice session, and I I learned a lot of things, particularly like what is group action, and how can we find and how to use, and what is the purpose we are making it. So it's a very useful session, sir. Thank you, sir.
Could you please introduce yourself?
I am Pumalai, working as a guest lecturer in Government Arts and Science College, Balu.
Thank
Okay.
you.
Thank you, Pumalai, for such nice words. Yeah.
Thank you, ma'am.
Good afternoon, ma'am. Good afternoon, sir. I'm Shikha Kumari, and I'm from Jharkhand. And I've completed my integrated MSc from Birla Institute of Technology, Mishra. And currently, I'm preparing for GATE exam. Ma'am, your session was really nice. We really got to know new concepts like Pomalai mentioned, and it will really help us for our upcoming exams as well as an interview, as you mentioned. So thank you so much, and thank you, ma'am, for taking out time for us. Thank you, Vinod sir, for organizing such sessions. Thanks a lot.
Sure. I mean, if you have any particular doubt, not related to this, but in general regarding exams and all, you can email me if you want. Okay, my email ID is there on my institute's website. If you look for my name, it is. You can always email me. I will try to be as quick as possible in responding based on. But yeah, you can always reach out if you need any help. Sure.
Okay, ma'am. Thank you, ma'am. Ma'am, please mention your email ID in the recording part that sir will send to us.
Okay.
Yeah,
So,
that we
I
can.
will write it in
That
the
we can see.
message so that will be better.
Okay, okay. We will share it.
Okay.
thank you, ma'am.
Okay, thank you. Yeah, it is given in the chat box. Thank you, Shikha. Others?
Yeah, thank you, sir.
Any others?
Ma'am, good afternoon, ma'am.
Yeah.
I'm Kali Shetty from Tamil Nadu.
Oh,
Yeah,
hello.
very, very pleasure to join with you. It's my pleasure, and it's a very interactive session. So it is very useful to us. All the things we know that a lot group action we don't know always, but now it is a. But after your class attended, it will be very easy to me. So thank you so much, ma'am.
Yeah.
Thank
Thank you.
Actually, what is your currently which course you are studying now?
No, sir. I'm preparing NET exam. CSIR.
Okay. All the best, college.
Yeah,
Yeah.
sir. Thank you, sir. Yeah.
Hello, am I
Yes,
audible?
Yeah.
yes.
I'm Anamika. I'm from Kerala. Currently, I'm preparing for IIT exam examination. Really nice session, ma'am. The group theory is one of my favorite subject, but it always make confusions on me. But the session is really nice, and you handle each question very nicely. Thank you, ma'am, for your valuable time, and we are expecting more sessions from you. And thank you for the email. Surely I message you. I have some doubts, so
Sure.
I think you will help me. Thank you, ma'am, and thank you, Vinod sir, for this nice session.
Yeah. Thank you very much.
Yeah, thank you, Anamika. Is any others?
Hello, ma'am.
Yeah, Atulya.
Hello.
Yes, Atulya.
My name is Adila. I'm from Kerala. Today's session is really nice. To explain the concept very clearly. Thank you, ma'am, for the session.
Thank you.
Thank you, Atulya.
Good afternoon, ma'am. Thanks for spending
Yeah.
your valuable time with us, ma'am. That was really a nice session. Ma'am, I have a doubt, ma'am. Can you clear it?
Okay, please.
Ma'am, can you give us some tips how to approach a problem in exam? That is, in what way we should proceed the problems, because we have lot of properties which makes us confusion in the exam pressure. Can you please give us some tips, ma'am?
So for group theory, it's not like, for example, in case of topology, we can say if we know the theorem stays, and a way of approaching a problem is similar more or less for any given question related to certain topic. But in group theory, that's not the case, because as I said that in order to relate that last question in group action question itself, in order to relate those one cycles with the group action of Sn acting on a set of numbers is also a bit intuitive, right? So in case of group theory, you have to like try to solve as much as question possible, try to see variety of questions, and at the same time I would say do not skip very basic theorems, and these Silo theorems and these orbit counting theorems. Such are theorems which are really important. They are very much more useful when we try to solve such numerical type questions. So try to kind of see those questions and try to work it. And please, I don't want to use this word, but if you are not intuitively understanding those statements, just memorize those theorems and see what formula or how those can be applied to different examples. And I would say to understand this properly, the group action part, I really like Santanam sir's book by Algebra. This book is really nice for understanding group action. I understood group actions from this book itself. So if anyone has doubts from group action, please follow this group. And apart from this, for any other questions, I would say practice and kind of having the hold on formulas and how to apply it. For example, the finding order of a product of element using the element order of element. Those are like very simple formulas, but sometimes it happens like in the exam, out of pressure or out of like anxiety, we forget that. But don't be like that. Memorize it so that it will be on like anyway. Agar you have to be solving problems, that's the only way. And books for different things, you have to follow books accordingly, which suits you. Just because somebody is saying follow this book need not work. Everybody has different way of understanding, every author has different way, and follow proper book. Yeah.
Yeah, okay, ma'am. Thank you, ma'am.
Joshua, please introduce yourself.
Ma'am, I'm Joshua Rigid from Tamil Nadu, pursuing third year mathematics, preparing for IIT.
Okay. Okay.
Okay, Joshua, thank you.
Hi, ma'am.
Yes, Abhishnav.
Yes, my name is Abhishnav CV, and I'm doing my graduation in B.Sc Mathematics from Government Arts and Science College. Ma'am, the session was really nice. Since I'm preparing for IIT JAM, it was really helpful for us to revising the basic concepts. So thank you so much, ma'am.
Thank you.
Okay, thank you, Vishnu.
Vinod
Fin-
sir, we
Yeah.
always want this type of interactive session. All the sessions must be this type. It will be very helpful to us. Some of the sessions sometimes it will be only lecturing, but we are liking this type of interactive session. It will be very useful to us, and we are enjoying to say some answer about this topic. So this we want all the sessions like this type of interactive sessions.
Yeah, Kalishwari, your suggestion is very good, but the teaching style may be different from person to person. And in our platform, majority of the sessions are not being handled by uh, trained teachers or faculty members. In our platform, the majority of the sessions are being handled by young research scholars. So, yeah, their teaching styles and skills may be different from person to person. But anyway, all of them are really passionate to help the juniors. That is the main point. Okay. Thank you, Kalishwari, for it.
I understand, sir. Okay, sir. Thank you, sir. Yeah.
If any others would like to share a feedback with me. Yeah, Shyama.
Hi, ma'am. I'm Shyama Kumar. I'm third year B.Sc Maths student at Aspirants University, Bangalore. Ma'am, it was a really nice session. I could follow most of your arguments. And thank you so much for sharing your email. Thank you so much.
Sure.
And thank you, Vinod sir, for conducting the session.
Yeah, thank you, Shyama. Yes, Ananda.
Hi, ma'am. I'm Ananda from St. Teresa's College, Kerala. Ma'am, actually, group theory was a little bit difficult to understand subject for me, but today's class it was very easy to understand. And ma'am, you start from very basics, so that it was also like a quick revision. And I hope you covered all the important concepts. So it also gave me a little motivation that group theory is easy to understand, and I hope I can go through it a little bit more deeper, and I have the confidence that to be able to study a little bit more by the session. Thank you, ma'am, for the session, and it was really useful for me. Thank you, ma'am.
Thank you. Thank you.
Yeah, thank you, Ananda. And the degree students can take this group action as your project, I think. In your degree project, it is one of a good topic that you can choose in abstract algebra. Yeah. Yeah. Is there anyone else to share a feedback?
Hi, ma'am. Good afternoon. My name is Vandana, and I'm from Kerala. So, first of all, thank you so much for this session. I'm sure this was a great help for each one of us. And once again, thank you for sharing your knowledge, effort, and time with us. Thank you.
Thank you.
Okay, okay, once again, I would like to
I
express.
want to say something. Yeah.
Okay, yeah.
I would like to
Yes.
say thank you, sir, and all the best for everyone joined here for your respective exams, which you all be opting for. And yeah, and you are all lucky to have Vinod sir here to guide you and conducting such wonderful sessions for you, because it might look like he's just hosting a meeting, but that's not true. Like he has to set up and approach like in to contact all of you for everything, then also to be in contact with us, also to ask us. I mean, for in my case also, he asked me
for like when to fix time, okay, and also it takes effort from his end as well. It might look like just hosting a meeting and listening. No, that's not true. It takes effort, and we all are lucky that he's here and helping you and us, helping us also. So it's really thank you, sir, for opening this platform for students and also for us to share our views.
Siddhi, when did you have joined in our community math aspirants?
I think long
In your
back. I
MSc
don't know.
time or MSc time or?
Maybe MSc. Yes, MSc time. Yes, sir.
It's very nice that. And I would like to express my gratitude to Siddhi, especially these young people, young research scholars are helping me to conduct all these things. So without the help from many people like you, I cannot move or I cannot run this community in this way. As you know, we have started since 2017 and now it is almost the 7th year.
Yes, sir.
So you just told that you are joined in this community during your PG. So like that, many people, many of the resource persons coming in our platform nowadays are actually started their math studies from our group itself, from their degree or PG days.
Yes, sir. I mean, I was part of the group even before I cleared my NET. So yeah, it's long back during my master's. So it's been more than 5 years maybe now. I am part of the group. Yes.
So thank you, Siddhi, once again, and wish you all success in your research career, and hope that you will be with us in future also and engage more sessions in our platform whenever time permits. I know that you are very busy with your research. I think you are now in SRF, I think, in the 3rd year.
Yes. 4th year, sir. My 4th year starts here.
Okay, so there will be a lot of pressures as a part of research and all that I can understand. But whenever time permits, please help me by engaging in this type of problem solving sessions. It will be very helpful for our juniors.
Sure, sir. Sure, sir. Yeah.
Okay, thank you. Thank you everyone.
Thank you. Thank you all. Yeah.